Today, we introduce to you AutoFeat, an Android app that can detect different features and stages of diabetic retinopathy and also provide an interface for doctors to mark out the spots of different symptoms. Diabetic retinopathy is the most common diabetic eye disease, which is caused by the changes in blood vessels of the retina and accounts for 12% of all blindness. However, most of them would have been avoided if detected early and treated with laser. Since diabetic retinopathy displays no symptoms at an early stage, it can only be detected through retinal imaging using modern imaging devices such as fundus camera. As diabetic retinopathy becomes severe, vision will be greatly impacted and may eventually lead to blindness. However, the detection process is completely manual and time-consuming. It requires a trained doctor, clinician, and technician to take the image and examine it for many symptoms. This process of review and examination takes up to a few minutes to hours depending upon the severity and condition of the disease and the number of images or patients seen at one time. Also, due to the lack of boundaries for certain features, the qualification of these features requires the feedback of more doctors for us to acquire an accurate algorithm.
In terms of algorithm, the major methods being used here are SIFT, K-means cluster, and support vector machine. Given a single retinal image, the first thing we do is to apply SIFT to obtain feature vectors of dimension 128 by 1. Depending on the complexity of the image, a large number of feature vectors might be generated. To reduce the number of vectors we have to deal with, we will then apply K-means cluster and use k is equal to 1. After clustering, we will be left with a single vector of size 128 by 1, which describes all the features in the original image. Once we know how to describe an individual image as a single vector, we increase the size of our data to include n normal images and m abnormal images. First, we process every normal image using the technique mentioned previously, and then we'll be able to get n vectors of dimension 128 by 1. We can put the vectors together in a matrix form to obtain a 128 by n matrix. We do the same thing to the m abnormal images, and we'll be able to get a 128 by m matrix. Both of the matrices will be fed into SVM, which generates a prediction model. Now, we have completed the training process. To test our model, we decompose the test image into vector using the previous method and feed the vector into the trained SVM. The SVM will generate a binary prediction on whether the machine thinks the image is normal or abnormal.
What we envision the app to do is to load an image from gallery and applies the image processing techniques we talked about earlier using the server. After analyzing, the app will be able to inform the user if the input image is considered to be normal or abnormal. If the image is abnormal, the user will also be able to mark on the image in addition to the processing result. To proceed our work from this semester, we're planning to make use of multiple prediction algorithms combined together to further improve the sensitivity and specificity of our model. Besides, we're also designing a more sophisticated feedback toolbox that allows doctors to mark and draw on images more freely.